So welcome to this conference, and I'm looking forward to hearing from you. There's probably a lot of people who have a lot of history with GPS and GNSS, and feel free to throw in your comments as we go along. So why did I call it 40 years of PNT? Well, it's actually more than that. I remember, gosh, this is so long ago, but in 1983, attending my first GPS conference in Rockville, Maryland, and seeing the Trimble 4000, the WM101, for those of you who know what those things are, hearing Colonel Brad Parkinson of the GPS Program Office speak. And the truth of the matter is that positioning, navigation, and timing have been going on for a long time, but GPS started to put emphasis on it in a way that we haven't seen before. So looking backward and forward, the question is how? Well, as far as forward is concerned, Gavin's already mentioned many of the speakers and topics that we covered in terms of the constellations of satellites that are up there that make up the collective term GNSS, where we had to spell it as GPS a long time ago. Talk about advances in receivers, receiver technologies, and of course the various kinds of applications. So I'm not going to spend a whole lot of time there except to kind of make the connection. So why do we look backward? Well, we look backward to encourage, because I think when you see the pace of development and the kind of development and the responsiveness of development, it's a really important thing to help people who are in the space today, or maybe just starting out, understand how things can go. To understand all the very many out-of-the-box applications that developed that nobody had dreamed about as GPS was going through its birthing starting in the 70s. Because I think it can help us avoid trouble in new applications. Why learn something again if somebody has already learned it already, as long as they've done a good job of educating us. And to help us see that the trend to here is an indicator, but probably less steep than the trend from here. So how did we get to this place? You know, what needs was the technology fulfilling that existed at the time GPS came about? How did the innovators run with the ball once GPS did come about? So PNT is a term that has been thrown about a lot, especially with GPS. And since GPS, we have many organizations within the US government that are concerned with PNT. And we take these things for granted today. Prior to GPS, being able to get position, to do navigation, or to get precise time was either slow, inaccurate, or used huge computational resources, all of these. Very often people had goals or desires, not always governments, but people desired these things. But most of the time people went, well, maybe someday. It was kind of an aspirational thing. Nobody really knew how we were going to get there in terms of better. So I said 40 years. Well, this is a little bit more than 40 years ago, even though this fellow in the picture is probably a more modern type. But what you see here are the Greeks came up with the idea of an astrolabe, which was basically a circle which was oriented to the vertical, meaning the direction of gravity, and then you had a sighting needle or line. You could sight the pole star. And if you could sight the pole star, yes, there were a few adjustments that had to be made because the pole star is not exactly at the pole, but you could determine your latitude. So people were good at determining their latitudes very early on. Of course, you have to remember they just sat around eating grapes, so they got to observe things like shadows and they saw what happened over the course of a day, of a month, of a year, and started to put things together. So this fellow here is de Champlain, a famous explorer, and he actually used, so this is a statue of him, obviously, not him in person, but he's using an astrolabe to figure out latitude. Longitude was a much more difficult problem to achieve. And really, there's a famous set of articles and books. You can look it up on John. There's a fellow named John Harrison who came up with the first working chronometer that won a prize awarded by the British government. And it was the first attempt to motivate timing technology in a really serious way because it was a very big prize. And even though the prize was for timing, it was actually to be able to determine longitude because nobody knew how to achieve longitude. And the idea here is to say, okay, the time where I am is such and such. If I was at Greenwich, but I'm not at Greenwich, I'm west of there, so I can observe things in the heavens that tells me where I am. If I have a book that tells me where a heavenly body is going to be at a certain time on a certain day. I'm not going to go through this in detail, but that's basically the idea for longitude, which involved precise timing. Now, classical navigation using those kinds of things was done mostly at sea, but there were also explorers on land, and then when we get into the 20th century, in the air, generally executed with a chronometer and sextant, and on moving platforms, depending on how rough the sea was, 1 to 5 nautical miles was probably typical. On land, especially if you're using tripod-mounted instruments, perhaps you could do 500-meter uncertainty. So here we have a sextant, and we have what's called a split screen. Guess what? They actually had split screens with sextants. We think of it as a digital technology, but they used it to sight the horizon, which meant we were orienting it to the horizontal, and then we sighted heavenly bodies, and the sextant was used using a double and sometimes triple reflection method to get the angle from the horizon up to the heavenly body. So this is quite common today. It's taught to navigators in the military. It's taught to a lot of civilian navigators who want to learn how to do it because it's always a backup. The picture on the right is actually a sextant being used aboard a KC-135, which is an air refueler, and they have a port in the ceiling there of the cockpit. I think there's another word that flyers use for ceiling, but anyway, they can observe the stars while flying. And I put this picture in because when I was preparing for this talk, I found this just accidentally, and I had to throw it in to give honor to my daughter, who is a pilot in the Air Force, and she actually flies these types of aircraft. And as the junior member of the flying crew, she was always responsible for the backup navigation system. Observing celestial bodies with precise timing also then enabled with precise instruments and ephemeris tables to get precise positions to within fractions of an arc second of latitude and longitude, determine things like the deflection of the vertical and azimuths to other points. So on the right, for those of you who are long-timers in the profession, we have what used to be called a wild T4, and they could be used to all kinds of purposes, but it meant that as we started to use better and more technology, we started to discover these subtle things such as the deflection of the vertical, which I'm not going to do a tutorial on, but I want to point out that these are important things as we use this modern technology today if we're going to do certain kinds of precise observations. So the geographic position on a sphere was pretty easy. You know, the philosophers, they learned things like spherical trigonometry and geometry. So it was pretty easy for them to figure these things out. It literally, I mean, I don't want to minimize the thought and the effort that it took for them to get there, but really they were doing PNT research and development even back then. All right, so all of a sudden we're going to jump forward to the 70s, and we had this thing where nobody really was that concerned with what we call georeferencing. Where are we on Earth? Yes, there was surveying and mapping, especially when we did property boundaries, or if we had a construction project, an engineering project, where we needed to know where everything within the project was contained. But it really didn't matter how it related to something else. So coordinating surveys was not considered all that important at the beginning. What happened then was the DoD, the US Department of Defense, decided they needed to start using better technology to locate their people, their armaments. And they wanted something in the 30 to 100 meter range, which was extremely radical, especially if this is going to be done pretty fast. And the scientific basis of this came actually from observing the Sputniks. So you can thank the Soviets, you could say, but it was American scientists, I'm sure there were people all over the world doing this, who started tracking the signal of Sputnik and discovered they could observe the Doppler effect. I think some of you know what that is. You know, we talk about the train, how it sounds, how the whistle sounds as it comes towards you, and what it sounds like when it goes away from you. And so they developed a system called Transit, which was actually used by the Polaris submarines. They could come up to periscope depth, extend an antenna, and figure out their position, which was really important for the purpose of being able to deliver their missiles to a particular target. A byproduct is that surveyors then started using it. And there are probably people in the audience who, if they didn't use transit, probably were aware that transit was being used to determine position. Maybe a meter, maybe a couple of meters, rarely sub-meter, but good enough for surveying in remote areas like Alaska, geophysical surveys, and so forth. So this was probably although people will argue, the beginning of satellite surveying. Now, what they discovered is things could be done so much easier and so much better if we could do it with gyros and accelerometers and this and that. And so they started doing it. The interesting thing is a gyro in those days, I'm talking about the 1980s, was probably $1 million, and people were still investing in things like this. At the same time, very long baseline interferometry was being used where radio telescopes were being pointed at quasars to determine transcontinental and intercontinental distances down to the centimeter level. And so people were familiar with this technology or this methodology. And so GPS was designed trying to take all of these ideas into mind. GPS was rated to deliver about 30-meter positioning for the military, about 100 meters for civilians. But early surveying receivers using these things like interferometry came up, if they were using 2 receivers, to be able to get much better positioning accuracy than a civilian navigation receiver were. And so for people where time and expense was not critical, all of a sudden GPS got to be a really important technology. Now you can see here in this diagram that in those early days of GPS, at a particular point on Earth, as the Earth rotated and the satellites moved around, the number of satellites visible varied. But the thing they knew is that they didn't need more than 4 satellites to be able to do positioning. Now, more than 4 was better, but there were also other early users. So timing, precise timing of networks, computer networks, broadcasting networks, power generating networks all need precise time. And because of the atomic clocks on board the GPS receivers, they started using it right away. People needing to do marine navigation could say, well, I'm just going to assume I'm at 0 height or elevation, and started using it with fewer satellites. With surveying, we pretty much needed 4 satellites, but if we could get them only between 10 o'clock at night And 6 in the morning, that's when we went out and collected the data. We didn't mind about the time back then. But this was nothing like a navigation receiver, and they were practical for long lines because it also then took about the same amount of time on those new 8T computers to then process the baselines. So control surveying was what it was primarily used for. In the mid 80s, we went from 4 satellite receivers to 5, then to 6, and I remember those were big news when they jumped. And all of a sudden we had umpteen, and so 16, 32, 64, and today 128 channels would not be unusual when you consider that they're receiving 2 different frequencies from each satellite or more. The big problem back then is that the receivers couldn't be used. But they also couldn't be used in real time. So the holy grail then, because people always wanted more, was real time and kinematic uses. So using the 2 basic frequencies of GPS, which are called L1 and L2, instead of using just the positioning codes, they started tracking carrier phase. And all of a sudden, they started to deal with what's called integer ambiguity. And this ties back to Gavin's little giveaway box joke that he had at the beginning of this conference. So the integer ambiguity has to do with this. To be able to measure positions really accurately at the centimeter level, it wasn't enough to use the navigation positioning. We also had to track the carrier wave, which means we had n times the wavelength of the GPS carrier wave for L1 that was 19 centimeters. And then we had a partial wave, and we counted these continuously. And this is how we started to resolve. Keep in mind, we were observing 4 or more satellites. So the GPS receiver had to do a lot of computing and counting, fairly basic math, but a lot of it all at the same time, and then do least squares fitting to all this data. So it didn't become very long that they could deliver centimeter level results. But other people then found that they could take the navigation receivers, tie them together, and get differential systems where absolute positioning was not important to the 1 to 10 meter level. And this made everybody look up and see that finally they could get positioning on a lot of things that they'd never been able to get before. Now, GPS basically measures ranges, and that's why I have this $50 word up there, multilaterative. So multilateration, and it simply doesn't, what if you're a surveyor, we call a distance-distance intersection. But it also had to be passive, so no two-way communications, because there was some development that was done in various parts of the world to do that. So all the brains were either in the satellite or in the control segment, which is why we had 2 and sometimes 3 atomic clocks in the control segment on each satellite, and an awful lot of computing power and awful lot of uploading of data that went into the satellite that was then beamed back down to each receiver. But there were problems to overcome, things like tropospheric refraction, ionospheric refraction, antenna phase centers, because they move with azimuth and elevation, what we call multipath, which I've kind of tried to portray here, and a whole bunch of other things, and this is just some of them that were in the system. And so there's a lot of work that went in, and a lot of the money that goes into the cost of a GPS receiver that you pay for is actually the software development, because most of these things were resolved using software. But as this went on, we discovered more problems, because GPS had its own coordinate system called the WGS84, and then this data needed to be projected on a plane, because most people are used to looking at maps which are flat. And so what happened is that when you survey with GPS, whether you like it or not, you become a GPS surveyor. However, most practitioners are not fluent in geodesy, and so this has caused a fairly burgeoning field of educating people on some of these topics. One of the most important things is that GPS broadcasts its position in what we call Earth-centered, Earth-fixed coordinates. And so this makes the math very easy for the GPS receiver to do. So it's X, Y, and Z, and then it's converted from there into latitude and longitude. But you can't be too ignorant of the technology. It's too easy to use it and deliver incorrect or inconsistent results. And so there's a lot of things like multipath that I talked about that have to be understood before you can decide that your measurements are any good. And it also requires an understanding of the technology and geodesy and projections. Because when you don't combine them all, it's really easy to come up with a value that that you measure with this technology and assume it's correct when it may not be. In the meantime, the Soviets play catch up with GLONAS. It was pretty opaque, and of course they were simply copying the US. They were a few years behind. The US launched its earlier satellites in the late 70s. The GPS, the GLONASS satellites went up in the early 80s. There's some other differences. Each satellite broadcasts the same code, but at different frequencies, which is exactly the opposite of what GPS does. But it also used a different datum from GPS. But some people liked it because it meant that a DoD, US DoD system, which could be controlled at will by the US, is not could then be subservient to the aims of the military, and so they were happy to see another system go up. Today, it's a useful supplement because we basically doubled the number of satellites in the sky. 2005, Galileo shows up with another 30 satellites and expected to be fully operational soon. And there's differences again, but the good thing is we had more experience integrating different systems to provide a consistent result to our users. Some of the more frequencies and more signals were added, but some of the services are not free, which is the first time anybody providing global navigation satellite systems went into that. And then finally, the Chinese came up with Beidou. Beidou, or sometimes it's called Compass, began originally as a regional system in 2000, but with BDS-3, you have a fairly complex grouping of satellites. You can read this on your own. It's close to fully operational, and it's now a worldwide system. I should also mention that we have at least 2 other systems, one in India, one in Japan. Navic covers a section of the globe. You see it listed there with 7 satellites. And Japan covers a smaller section of the world, but it's developed as a supplement to GPS and to improve timing. It's 4 satellites currently, but expected to grow to 7 by 2023. So all these satellites gave us faster times to fix. I still remember when GPS first came out, 20 or 30 minutes before we had our first fix with our static receivers was pretty standard. Nobody complained about it. Nobody complains today when first fix is under a minute. And nobody complains when you go under a bridge, you break lock, and you regain lock in a few seconds. And it used to be you had to wait another 20 minutes in the old days. So the receivers can be used in more hostile environments. And by hostile, I mean anything that interferes with the satellites reaching you or your receiver, and also that can block the receivers, because you need line of sight from your antenna to your satellite. The complexity of the processing has increased, but the great thing is Moore's law and everything. Computing power has increased together with reductions in size and power requirements, and so the technology has been able to keep up with these tasks. GNSS is little noticed by the average consumer, but for the professional, for the higher positioning capability, it means that pretty soon the average consumer may be able to see 15-centimeter positioning, maybe with a special attachment on their phone. The GPS the professionals using it should be able to get reliable positioning that's even better, but faster. And the thing is that now that we have more problems that come with the progress. One of them, for example, is if you're positioning yourself as a consumer on the surface of the earth and you go out to a known point and you hold your phone over it and you see a mismatch of more than 15 centimeters, they're going to say something's wrong with my phone or something is wrong with the published data, but it may not be either of those, because datums and projections still have to be figured into the solution, where it can be safely ignored, because whether your GNSS navigation receiver gets you 5 meters or 2 meters or 10 meters, it's really not that important, because chances are the datums and projections issues will not be that large. So getting them into the same environment is an education problem that may come up for the average consumer, but certainly for the user at the professional level, extremely, extremely important. So for surveying and mapping, the stationary observation of baselines is still the gold standard, but real-time systems with informed use can be used to solve many, many problems that were not anticipated when GPS first came out. The problem is that when you get a position with any of these systems, they don't carry a label saying this is how accurate it is, or this is how it was measured, or this is what PDOP was at the time. And people go, well, what the heck is PDOP? Because people have stopped worrying about that. Nobody does mission planning anymore to figure out where the satellites are going to be in the terrain that they'll be using it, or not many anyway. So there are those things that are very hard, because the receivers try to estimate their positioning uncertainty, but they are not to be taken to the bank. Now, GNSS is not universal. Yeah, sure, GNSS on the phone works indoors, but it is not surveying or mapping quality. Why? Because the signal is bouncing around before it gets to you inside a building. When attached to construction equipment, it's real easy then for the uninitiated to make more mistakes, bigger ones, and faster. And that is why informed use, in my opinion, is an important part of GNSS in the AEC space. Building in integrity monitoring into the system is always a struggle, trying to find ways to do that, and to find ways for people who are users of the system to pay attention to the integrity monitoring is always going to be an issue, although things are happening that can make things more difficult to ignore. So I don't think I need to tell you about all the applications that currently exist with things like geodesy, tectonics, and engineering surveys. Here's a map modeling continental drift, but we have things like Earth monitoring, using a drone with LiDAR, or machine guidance, are all applications that GNSS facilitates. If we didn't have the GNSS, it would be a lot harder using other positioning technologies. So I've done a laundry list of some of them, only because I think each of these can drill in and start to exploit their spaces even more. For example, when GPS was only a differential GPS, was maybe only a 2-meter system, utility companies had already started using the GPS coordinates as a unique identifier of points in their system, because they were pretty sure there's nothing else within 2 meters of a particular transformer or cabinet or pole or whatever. But I think that's going to improve over time as the positioning accuracy improves, as long as we have labels that tell us how good that positioning is. We have all these robotic systems. I've called them airborne unmanned systems, sea surface unmanned systems, land unmanned systems that are going to go around doing all kinds of things, including the next thing on my list on the right-hand column, which is automated site work. You could theoretically have a system where robotic vehicles survey the land, send the data back to a remote location, site work is designed, and then the vehicles that are on the land that are automated with machine guidance then go to work changing the landscape. Geofencing is an extremely important part that I think is going to become even more important in the future for all kinds of reasons. Security and theft deterrence, only two of them, and safety of life machine limiters, making sure that a crane doesn't hit a high tension line, making sure a hoe doesn't break into a high pressure gas line. As the map quality of the mapping increases and the databases are all in the same environment, then you can actually start to use these devices. Now, while GNSS use will grow, it can't grow without integration with other technologies. So all kinds of PNT aiding technologies are important. Sometimes it may only be one. For example, you probably know about GNSS being used on graders, but they also use lasers to help control the vertical dimension in that 3D space. Integrating with other measurement technologies, integration with communication technologies, both transmitting and receiving. Various kinds of artificial intelligence to evaluate a situation and then execute whatever it happens to be. And then finally, virtual reality and augmented reality and fused vision, I kind of treat them all in the same space, is starting to make it easier to envision our projects and then to build them. So how will it be considered? When I say below the surface, I mean the GNSS is not always there on the surface. A good example is our cell phones. Not everybody thinks about their cell phones having GPS or GNSS on it. And yet we rely on many different functionalities in our phone that would totally not be operable if they didn't have the GNSS component. A better example may be the use of GPS or GNSS to describe the device in our car that we use to navigate from place to place. It's really a misnomer because it's really a GIS system, a geographic information system, where GPS or GNSS is simply the pointer or the cursor that tells the software where you are so that it can show you the appropriate information for that location. So GNSS is an essential part, but it's a small player. That doesn't mean that it's small in terms of its importance, but it's a very small player that sometimes is simply silent or invisible. And that's where we're going to see a lot of the changes happen in the future. So in geospatial and AEC alone, it is likely that the innovation lies ahead to enable productivity at a far faster rate than it has already enabled today. And so with that, I am going to talk. Hope you enjoyed this little walkthrough time, because that's what it was. You could say, oh, he's taking us back through dinosaur days, and in some ways I was, and be happy to answer any questions.
Well, Joe, I can't thank you enough. That was the perfect setup. In talking about the evolution and talking about how that evolved into the different applications, you touched on a lot of things that are going to be presented in the next 2 days. You talked about the, precision getting easier for more people to do, although with the caveats about understanding the geodesy. But even that is being, people understand that, the developers, and they're trying to build in the checks and balances, and with mixed results. I still occasionally get a phone call of somebody going, why am I 130 feet off, vertically? Well, okay, there's a thing called a geoid, but A question I get a lot, and you probably do when you speak about this at seminars and associations, is, when is the phone going to get the centimeter, just like the surveyors? Well, you and I both know that's almost an impossibility. But do you, yeah, do you think people still hold out the hope that just their consumer phone is going to be able to give them a centimeter?
Oh, I don't think it'll be a centimeter, at least not in the near future. But I can see 15 centimeters. Here's the problem, though, and I say 15 centimeters because for those of you thinking uh, feet and inches, that's about a foot. And the big problem there is the problem that I still remember when RTK first came out. People loved it because it gave us coordinates that displayed to maybe hundreds or thousands of a foot or a millimeter. And people took that to the bank. And just because we see 1 foot or 15 centimeter resolution doesn't mean it's 1 foot or 15 centimeter accuracy. And so, but there is that ability to resolve positions that well. And the hard thing, I think, for consumers out there in the real world, so to speak, whom we all serve, is that I'm not sure they understand the difference between accuracy and resolution. But we need to make sure that the users, just because it's becoming easier and easier to push a button and get a position, understand that what they see on the display has to be more and more carefully explained to their customers or clients.
Very true. The education part of it. Just a side note on about the phones. I'd recently been interviewing a firm that uses phone position data for forensics, for accident recreation and public safety investigations. And they said, yeah, okay, you got a position on your phone. Let's say it got a centimeter. What pocket was it in? Which way were you faced? What multipath did you have off the buildings? So the antenna in here for the GAPS or GNSS is actually pretty crummy. You mentioned about adding peripherals. So this is an antenna that you can add to your phone. But the GPS chip in the phone, and I remember buying one for $5 and hooking up an antenna on a processor to build my own, is not very precise to start with. Is it getting augmentations from a real-time network or L-band PPP and so on? But there are options now, receivers as a service. You download a software-defined receiver into the phone. It runs on the processors. And if you have a peripheral antenna, I've actually tested it, and you can get down to centimeter. But that's a lot of moving parts. But as you said, the key part is, well, GPS can tell you where you are to the millimeter, but it won't tell you if it's the right millimeter. We were discussing last night about this. You see firsthand the challenges in even surveyors, that are masters of precision and accuracy. Before the advent of GPS, a lot of us never even had to think about geodesy. We were working in a relative mode in a subdivision or in a city, tying between monuments, turning angles with a total station. Now you run, you're the principal in GeoLearn, and I've looked over your catalog, and you touch on geodesy quite a bit in those fundamentals. I don't know, you've touched on that need. How do you think that's going amongst surveyors? Do you think they're, and others, in the GIS community, do you think they're catching on to the fundamentals of the geodesy that they need?
It's hard to know for sure, Gavin. There is a big tendency to want to resist learning new tricks, especially as the dog gets older. And so I think maybe our saving grace is that we have younger people. And when I say younger, I mean people who are new to it. So they may be old in terms of number of years they've lived, but maybe younger in terms of being introduced to what we are trying to accomplish as surveyors and mappers, and pay more attention to all the fine points like geodesy, which actually is not a fine point. It's pretty basic. GPS would not work if the people who designed GPS didn't understand geodesy. The problem is we get results that sometimes don't make sense. I still remember an airline pilot one time asking me how come when I turn on my little hiker GPS that he had, and by the way, I told him it was illegal to run a radio in the plane because he was riding along as a passenger. And he said, "Oh, it's only a GPS receiver." But he said, "How come when I'm flying to Tokyo, that when I look at my GPS, it's really good for horizontal position, but my altimeter and the height displayed by the GPS are very different." And I think it took the rest of the flight to kind of explain it, and I'm not sure he still got it. So that's the problem we face, because it's not just our clients, our customers, the people who use our information that we generate from doing all this, and people who rely on it. Now, I still remember back when Dave Zilkowski was director of the National Geodetic Survey, he pointed out how many people are going to pay attention to the datum of the elevations provided to people in areas prone to flooding. Will they be able to correctly match up that information to what the local tides are? And so it gets to be a really complex problem that has to be understood at many different levels depending on the application. I don't know if I answered your question.
You did. Hey, and as I predicted, the questions come in right at the end. So we got 2 quick questions, 2.5 minutes each. Julia Subcheck at Compass Data, who we're going to hear from later on, she said, your thoughts on the modernized National Spatial Reference System. The National Geodetic Survey is going to update our spatial reference system the way Australia did a few years ago, and then the press said, oh, yeah, they have to update it to keep up with GPS. It's actually kind of the other way around. But she asks, how important is the vertical datum that it will be more accurate by the use of the gravimetric data?
Julia, just so you know, panelist to panelist, you're supposed to throw us softball questions. So please remember that. But go on. I really think that we're getting to the point, especially when you figure that satellites are being used more and more, in addition to gravimeters, to detect gravity, that knowing where the geoid is definitely an important thing. I keep telling people all the time, just because you have GNSS does not mean that you can accurately, for purposes of design and build, use GNSS always the way you think you can, just because it's more accurate horizontally, because you may have subtle changes. All depends on how good our geoid model is. So if the geoid model is really, if the geoid or the determination of the geoid is really good, and then we can provide a really good geoid model to the people using our systems that are capable of using the geoid model to its utmost, then yes, we start to see more applications where perhaps GNSS can be used in what we call the vertical from a traditional surveyor's viewpoint.
Okay. A quick question from Dave G. Can you discuss how GNSS and terrestrial integration have evolved and how it might affect AEC digital data work processes?
I'd say stay tuned to the next 2 days, Dave. It's going to be hard for me to summarize that in 2.5 minutes.
Right on.
I think plenty.
This is a question we might not have time to answer, but I really would like to hear this discussed a bit more. Gabriel I said, do you think that, for instance, a smartphone GNSS high precision, including inertial sensors and camera, will provide a shared database and create something like a Google Earth virtual world in real time?
Well, I really think that's feasible. I didn't want to talk about that too much because I think we're seeing various process of democratization happening with these new technologies. I think we have to give credit to the the internet for part of that. And I don't see why that can't happen. The problem is who manages it? How do you tag data that goes into it if you have a crowd contribution to this database, right? Because we have people using different technologies, using different constellations perhaps, certainly using terrestrial technologies as well as global navigation technologies, and how you manage that can be really complex. I don't think it's an insurmountable problem. I'm not expecting to see that happen in my lifetime. I can see some steps in that direction, however.
Mhm. It's not necessarily the technology, but in some ways policy and social mores. There was an exercise one entity did that they took all of the photos uploaded of Trafalgar Square on a during the tourist season and made a 3D model of it before midnight. So you had a live 3D model of Trafalgar Square crowdsourced off of social media. There's a question from Gilbert, but I would like to get to that later. That's a great question.